Right, so let's do the tutorial now for this topic that we have just finished. It is like tutorial 6, right? Right. The first question, I think we've just done it in the lecture. So design a 2-bit adder using one full adder and one half adder. We did it, right? So do you remember when we take this? So we said the first stage could be half adder. We have A0, B0, or I can just use 2 full adders. So I can use a full adder and then put 0 here. And that's it. You have the answer. It's already on the... So design a 2-bit comparator. Question B is to design a 2-bit comparator. Now I want to design a comparator. So we'll have F, G, H, or you can call it X, Y, and Z. And then we have A and B. Those are 2 bits. So I want to compare A and B. So how can I design this comparator? So the question is to design it. How do I start? I want to design, so I need to compare A. So A has A0, A1, and B has B0, B1. What do I need to do?
Doctor, will the comparison be element by element?
The number as it is. It's not element. You're not comparing element by element.
No, I mean by like A0 and B0, A1 and B1, or do we have to consider all combinations?
The whole combination. So for example, if I have A is this value and B is this one, this is A, this is B. So is A more than B, or are they equal, or is A less than B?
A is more than B.
A is more than B in this case, right? Because this is 2 and this is 1. Yeah, so if A is more than B, then the function that corresponds to this should be 1, which if we use the, let's say G is the 1, so this should be 1, the rest should be 0. So how can I proceed with this?
Make the truth table so you could find the expressions for F, G, and H.
Truth table. And this is the truth table, so I used X, Y, and Z here, yeah, which is fine. And then you get the expressions, and then you will use the K-map to get X, to get Y, and to get Z. Is it clear? So our inputs are like A0, A1, B0, B1, but we will consider them as like a full number. So first case, they are equal. So this means the Y here is 1. Is when they are equal. X is when A is less than B, and Z is when A is more than B. And then I will just look into all combinations. For example, the last one as well here, 1, 1, they are equal. So this should be 1 as well. Here, 1, 0, 1, 0, they are equal. So this should be 1. And here, should be 1. And so on. So I need to do all the cases, and then I will just do the K-map. I'm not going to go through this. And then you get the expressions. And then based on this, you draw the circuit. I just got the expressions here. I didn't draw the circuit, but you can draw it with 4. These are 4 inputs and gates. You can use XOR here as well. and so on. So this is, it's a little bit complicated circuit, but of course you can solve this with multiplexers, right? If we ask you to do this with multiplexers, so you can find X, Y, and Z using multiplexers. You can make it simpler. You can do it with a ROM to make it even simpler. Right, so this is for this question. Next one. So we have this circuit. It includes one half adder and one full adder. So we have input X, and this input is always 1 for this half adder. Those two inputs as well are always 1 for this full adder. And then we have S, CO, and C1. So we ask you to redesign this circuit to use the minimum number of components. So how can we proceed here? If you do this circuit as it is, you will be wasting resources. You don't need a half adder and full adder to do this. You can reduce the cost by using less components. So what do you think? How can we proceed with this? How can we get a better solution?
Using one full adder.
How? How do we get it?
The inputs of the full adder will be 2 of them is 1, and one of them is X plus 1, if it's possible.
Nope. If we start with this half adder first. Half adder, we have S and we have C for half adder, right? Are the outputs. And then what are the inputs?
0, 1, 1, 1.
And 1. Huh? The inputs for this half adder.
0 and 1 and 1, 1.
So we have just like one input that changes, which is X. The other one is constant, is 1. So I can just put X here. I can have, if X is 0, what is S?
1 and carry 0.
X is 0, sorry, X is 0, S is what?
1, because it's being added to 1, right?
Yes, it's 1 because we are adding 1 here. Because this is a constant, yeah? If X is 0, I'm just here in this half adder, yeah? If X is 0, S will be 1 because I will be adding 1, and C is 0. If X is 1, what do we get? Sum
It's 1
is
and the sum is 0 and carry is 1.
good. Sum is 0 and the carry is 1. Excellent. And that's it. So what do you think? What is S?
X bar.
Huh? S
X
is
bar.
equal X bar. And what is C?
Equal to X.
Equal to X. So basically I have X. I will just take X bar. I will get my S here. Right, this S. And then the C is basically just equal to X. So this is C. So I need just an inverter here instead of using a half adder. Right, if I move now on to the next one, the half full adder. Is the same here. So we have this S as an input, right? So I can just delete this and put S here. So if S, if I call it half adder, just to make S coming from half adder, SHA. If S is 0, what do we get?
Sum is 0, carries 1.
So we will be adding 0 plus 1 plus 1, right? Because those two are 1, 1. So 0 plus 1 plus 1. So yes, you are right. So we'll get sum 0 and the carry is 1. Now if S is 1.
Sum is 1, carries 1.
Sum is 1, carry is 1. So this is basically the, this is the SHI, yeah, that I'm using here, is this one. So what is the S for the full adder?
The same as S for the half adder.
S is equal SHA. So it's the same. So this can go to the final S, right? And then what is C?
This is 1.
C is this one, is the C0 basically, right? So should use C0 here, or CO. Yeah, it's the same one, yeah? So it's 1, it's always 1. So I can just have, and this is C1, yeah? From the previous one is C1. That's before. So just this one is always 1. And this is my CO, and that's it. So basically all this is just an inverter. And the rest are just wires. So I did this in purpose because you will, I think the homework, sorry, not the project that you will do, you will be designing an arithmetic circuit, and you will be looking for the best solution. And we get this when you design a multiplier or an adder where one of the inputs is a constant. So let's say that I want a multiplier that always multiplies by 10 or always multiplies by 5. So one of the inputs is always constant and one is, you get those cases. So you need to be careful. So you don't have to use a full adder like that and then have two of its inputs always 1. Because you can reduce it. So you can use, have a better solution, which I showed you here. So this exercise I did this in purpose so you can, and again, you will get this when you have one of the inputs is a constant. Right. Question 3, this is a multiplier. And multiplication in binary is again very similar to multiplication in decimal. So do you see here? Those are bits. Let's say that I'm working with 3 bits. So this is A, this is B. A is 3 bits, B is 3 bits. Is very similar to doing the multiplication in decimal. So we take B0 by A0, then B0 by A1, then B0 by A2. What do you think this? You can do it with which gate?
And
This is just a simple AND gate. So B0, 0 by 0 is 0. 0 by 1 is 1. 1 by 0 is 1. Sorry, 0. 0 here. Huh? 1 by 1 is 1. This is very simple AND gate. 0, 0, 0, 1, 1, 0, 1, 1. This is a simple AND gate. So those, we call those the partial products. Those partial products in binary, we can get them by just using AND gate. And then we continue with the similar as we say for the decimal. Then we go to B1, A0, B1, A1, B1, A2. And then we go to B2. And then at the end, we do addition, right? And that's it. So we gave you this. And by the way, when you multiply two values, as you can see here, I started with 3 bits, 3 bits by 3 bits. The final answer is 6 bits. So general case, if you do n bits, result is 2n. So you multiply two values of 8 bits, the result should be 16 bits, as you can see here. The question is to design a 2-bit unsigned multiplier. So we ask you to do the same, but for less complex than the above one, but just for a 2-bit instead of using 3-bit. So of course I can start with something like that. So we have A0, A1, B0, B1. So we do A0, B0, A1, B0. So we multiply those, and then we go for A0, B1, and then A1, B1. Is this clear? I'm just doing the normal multiplication as I would do it in decimal. And then we get the answer. So this will be C0, C1, C2, C3. We get C3 when we do the addition. So if there is a carry, so there could be a carry from here, and then when we add those two, I could have another carry, right? So what do you think? How can I implement this now? What do I need to use to get C0?
So C0, you just need one AND gate.
So C0 is very simple, just one AND gate, because I will be adding zeros here, right? So it's just a simple AND gate. So we'll do A0, B0, AND gate, I will get C0. So this is the first bit of the result. And then I will move on to the next one. How do I get C1?
It's going to be a full adder because you need the half adder because you still need the carry for C2.
There is no carry from C2. It's just an AND gate, right? So we have C0. Ah, sorry, here you said for C2. So what do I need to use? Full adder or half adder?
Half adder is 2 bits.
Yes, half adder. Yes, good. Sorry, I thought you said full adder because we need to carry from previous one. No, so okay. So, and what else? So it's not just half adder, right?
The AND gates.
So I need two AND gates, one AND gate here, one AND gate here, and then I need to do the addition, and then a half adder. So it's basically, it will be something like that. Another AND gate, and then this will go to a half adder, and then the half adder will give me C1, the next bit of the answer, and then this will give me the carry which goes to here, to the next one. The third stage. So what do I need here?
Again, half adder and one AND gate.
I just need a half adder here as well, and one AND gate. So this carry goes to the next half adder, and then I will need an AND gate as well. And this will give me C2, and this, the final carry will be the C3. And that's it. So you can design whatever you want, the size that you want, by just following the same. So this is the final answer. And this is what you were saying. So C0, we need one AND gate. So C1, we need two AND gates and one half adder. C2, we need one AND gate and one half adder. And then for C3, we don't need anything. It's just the output from the last one. And this is the full circuit. So we have A, B, and C. C is 4 bits. Because when we multiply 2 bits by 2 bits, I get an answer of 4 bits. And this is how it's connected based on what we did here. Is this clear? Okay, good. Last question is related to the negative value, so we should do this quickly. So what is the maximum negative number that can be represented using 8 bits?
2 to the power of 8 over 2.
Huh?
Minus 2 to the power of 8 over 2.
Sorry, I didn't hear you. Say again, it's minus 2 to the power
8 over 2.
Over 2. Over 2 is like this, right? So it's basically 8 minus 1 here. Is this what you mean, yeah?
Yes. But does maximum mean like maximum in the negative region or like magnitude?
This is a tricky question. So
that's what I mean, because if it's magnitude, then it's minus 1.
Yes, so this should be the answer, is minus 1. So minus 1 is always the answer, right? If we look for the minimum negative number, whatever this size, so it's always minus 1, because minus 1 is more than minus 2, which is more than minus 3, which is more than minus 4, and so on, right?
Yes.
Yeah. Oh, sorry, we say here, negative number. And the positive, what is the positive number? The maximum positive, I think maximum positive is clear, is 2 power. Here
16
we said,
minus 1.
I'm sorry, I was confused. We were with this question and I jumped to the next one, yeah. So I think for the first one is clear. You already answered it, so it's minus 1. The answer is minus 1. The maximum negative number that can be represented with any number of bits is always minus 1, right? Because minus 1 is more than the other one. Okay. The next one, what is the minimum negative number and the maximum positive number? So this is basically a question about the range. When we use 16 bits, we did this. I gave you the general case. So we say the general case, x is less or equal to power n minus 1, 2 plus 2 power n minus 1 minus 1. So if we use 16, we just replace the n with 16. And that's it. Right? So this is basically the range. In 2's complement, what do all positive numbers have in common?
The most bit on the left is 0.
Good. So the most significant bit, the MSB, yeah, most significant bit, or MSB, is always 0 for all of them. If the question was about negative numbers, then it's always 1. Okay, good. And then we ask you to convert the following decimal numbers to binary using 6-bit 2's complement. I don't want to spend time here. So we said using 6-bit. So if we take one example, 15. 15, you know how to do it. Minus 17. 15 is a positive number. You know how to find 15, yeah? So this is 15. Using 6-bit. So we said 6-bit, so we need to add 2 zeros. Right? 1, 1, 1, 1 is 15, and then we add 2 zeros. So this is 15. Now the negative values, minus 17. We need to find first 17. What is 17? This is 16, right? And then we add 1. is 17. But we are working with 6-bit, so I have to add 6-bit. 1, 2, 3, 4, 5. So I need to add a 0 here. So this is plus 17. Oh, sorry. I don't know why I put 5 here. Now I just need to do the choose complement. So we do the first complement first here. And then we do plus 1, which gives me 1, 1, 1, 1, 0, 1. So this is the answer. This is minus 17.
Doctor,
Yes.
I have a question. For when we have positive numbers, we're allowed to add leading zeros, but negative numbers, it's not allowed, yeah?
No, you cannot add. You will add leading ones. So if we say what is minus 4 in let's give you the previous example. So this is I lost it. Okay, it's fine. Let's give you another example. Minus 4. So this is 4 using 4 bits, and then we get the ones complement. This is minus 4, right? So this is clear using 4 bit. Now, if I tell you what is minus 4 using 5 bits, minus 4 using 5 bits, you don't have to repeat this again. If you know what is minus 4 in 4 bits, you just add leading ones. Minus 4 in 6 bits, you just add 1. Instead of adding zeros, we add 1. Do you remember when we talked about shifting, arithmetic and logical, and we said we fill with the last significant bit. So if the number was negative, you keep it negative. So basically you add ones. If this is minus 4 using 4 bits, you add another one. This is still minus 4 using 5 bits. You add another one. This is still minus 4 using 6 bits, and so on. Is this clear? Same for positive. If this is 4 using 5 bits, if I add a 0, this is 4 using 5 bits. And this is 4 using 6 bits by adding zeros. The same applies to negative values. Is this clear?
Yes, doctor, thank you.
Right. Next, if we let's do one of those and then we stop. Now if we give you the number and we tell you convert, now we give you the binary and we tell you what is this number. So for example, this one. And we tell you that what is this number. We are using 8 bits. The last bit is 1, so this number is negative. So, but what is the magnitude for this number? Minus what? We have 2 methods. You can either convert it back into, do the choose complement again here. So if I do the choose complement again for this one, I will get 1, 1, 1. 1, 2, 3, 4, 5, 6, 7, 8, plus 1. Zero, 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 0. And so you get back to the original number, and then you convert this using the normal method that we know of the when we look for what is the maximum or the minimum number, the minimum negative value using 8 bits. So this is minus 2 power 8 minus 1. Let's give you another example, just to avoid confusion, because this goes into the limit. I don't know if you get my point or not. Let's do 4. If I use 4 bits, what is the range? if we work with positive and negative numbers, we said x is less or equal minus 2 power 2, less or equal
3 though.
3. So this is the, so we know that this is 0.
It should be minus 2 power 3 though.
Oh, sorry, 3 bits. I want to work with 3 bits. 2 plus 2 power 2 minus 1. So this is correct, right? With 3 bits. We go from minus 4 to 3. Is this clear?
Yes, though.
Yeah, so with 3 bits, I'm just trying to work with less bits so you can understand. 0, 1, 0, 1, 0, 1, 0, 1, 2 zeros, 2 ones, 2 zeros, 2 ones. Right. So we say half of it is positive. So this is 0, this is 1, this is 2, this is 3. And then this is minus 4, this is minus 3, minus 1. So do you see the minus 4? Minus 4 in 3 bits is like the 4 in 3 bits, right? So this is the limit. Is like is the same code that we use for 4 if we work with positive values. So this is the same case here. So if I take the number, if I take minus 3 now with 3 bits, and I will tell you what is this. I'm working with 3 bits. It's very important to know with how many bits you work with. So we are working with 3 bits. In our system, we have 3 bits. So this is the number 101. And we tell you what is this magnitude. So we know that here is minus 3, but how do you get it? So the last bit is 1, so it's a negative number. How do we get it? We can either do the choose complement, again, here. So I do the choose complement even for a negative number. So I do 0, 1, 0, plus 1. Then I get 1, 1, 0. What is this? 1, 1, 0 is what? Is 3. So this is minus 3. So you just do the choose complement again, and you get the value. Of course, you need to convert this at the end. So you need to know this. Or if you want to work with this one, we can use the method that's, we know the method that's 1 by 2 power 0 plus 0 by 2 power 1. But here I don't do plus 1 by 2 power 2. I do this if the number was negative, positive. Here I will just do minus 1 by 2 power 4. So instead of doing plus here, I'll just do minus. And then if you calculate this, what do you get? You get 1 by 2 power 0 is what? Is 1 plus 0 minus 2 power 2 is 4, so minus 4. 1 plus 0 minus 4 is equal to minus 3. So you can get minus 3 immediately from this. So we have 2 ways to find this. So you can either do choose complement, and then you will get the positive value, or you just work with this method. In the last bit, because this is for the sign, this indicates that this is negative, I will just use minus here. And that's it. You get the answer. So you can apply the same for the other value for this question. For all those you can apply. So the last one is positive. You don't need to do anything. It's positive. You just find the method. So this is 0. So this is positive. Those 3 are negative. So you can find them using the same way that I just showed you. All right. So this is the last question for this one. So which is good. We completed this tutorial. I will put extra practice problems for you. Try to solve them.
Doctor,
yes.
Do you have the document for the homework? I have just one question, one clarification in it.
The homework, yes.
Yes.
Okay. Homework 2. Yes.
Yeah, in question 2,
yes.
This output, it has 2 connections, so it's a 2-bit output, yeah?
Yes, this is 2 bits. Always
Okay,
2 bits.
and for question 3, it says if it's majority 1, it should display 1. If it's majority 0, it should show 0. If there's no majority, it shouldn't show anything, or is there a default value?
No. If the majority, what we mean by the majority, when do you display 1? If the majority votes yes, which means we have 3 or more is equal. So 3 of the switches were on or more. Do you understand? So
Yeah.
if choose
What
3 or more.
confused me, after the sentence is that 0 should be displayed when the majority vote no. What about if it's 2 no, 2 yes?
No. I mean, if this has confused you, this is what I mean here. I mean, if you have 3 or more, you display 1. All other cases should be 0.
Yes, that's okay. No,
Is
thank
this
you.
clear?
Yeah.
Yeah. 3 or more is 1. All other cases, which means that the majority didn't vote yes.
Yes, now yes, thank you.
All other cases, yeah, okay, no problem. Okay, so that's it. So I will post the solution on Blackboard, inshallah, and that's it for today, inshallah. So we'll talk to you next session, inshallah.